We're very happy today to have Mina Aganagic from Berkeley. And as you can see, the title is Not Categorification from Mirror Symmetry.
Okay, thank you for inviting me. It's of course an honor to be here. So this is about two works, one of which appeared last year in April, and the other one which is should appear any day now. Okay, let me just see how I have a problem in that. Okay, here we go. All right, so in 98, Khovanov showed that there's a deeper structure that underlies a link invariant that Jones found in 85. So Jones associated to a link a polynomial in one variable such that links with a different polynomial cannot be smoothly deformed into each other. And the coefficients of Jones's polynomial are always integer. He defined the polynomial in a simple way by explaining how it changes as a pair of strands cross and giving the value for the unknown. Khovanov explained that one can recover Jones's polynomial as a shadow of a cohomology theory, which to a link associates a collection of vector spaces, which are graded by a fermion number and an additional grading, which we'll call equivariant, an additional integer grading. These vector spaces are themselves link invariants, and their equivariant Euler characteristic is the Jones polynomial. In 1988, Edward Witten explained that the Jones polynomial comes from Transcendence theory with a gauge group based on Lie algebra SU2 with an effective Transcendence level kappa that determines the value of Q. Jones's polynomial, as he explained, is the expectation value of a collection of Wilson loops in the fundamental representation of SU2, supported along the link components in Transcendence theory in flat R3. This leads to generalizations of Jones's polynomial where one varies the Lie algebra and the representations. The resulting link invariants are known as the quantum group invariants. The relation of Witten's link invariants to quantum groups was developed by Reshetikhin and Turaev shortly after. I will explain that Khovanov's construction also has origin in physics and one that generalizes to all gauge groups in parallel to what Witten did in 88. From string theory, in fact, so this explanation originates from string theory. And in fact, one derives two approaches that are related by a version of two-dimensional mirror symmetry. It turns out that the resulting theory is solvable explicitly. Two-dimensional physics enters here because the descriptions we will get come from two-dimensional theories associated to link times time in R3 times time. More precisely, as it comes out of string theory, the theory turns out to be equipped to describe not only links in R3 times time, but also R2 times S1 times time. But that won't be very important for us today. The theories come from two-dimensional defects of the six-dimensional 0-2 conformal field theory, as was anticipated by in works of Oguri and Waffa in 1999, and also Gukov, Schwartz, and Waffa in 2004. The implication of their works is that was that if one is able to understand how to extract spaces of BPS states from the 0-2 theory with defects, they will be Khovanov homologies and their generalizations. The six-dimensional or five-dimensional approach to this problem is being developed by Edward Witten. The approaches I will describe are complementary and solve the problem from perspective of two-dimensional theories on defects themselves. The fact that the problem is tractable at all, let alone solvable, is very surprising. The theory we will get from string theory will be, in the sense of computational complexity, better than Khovanov's, even for the simple SU2. The reason, from my perspective, why Transcendence not invariants are interesting is not so much that knots and their invariants are interesting, but rather the wealth of mathematics and physics connections that one discovers once one understands them. The fact that the structure arises from a deeper theory will no doubt lead to many more connections. We'll see one of them here, to solvable but highly non-trivial examples of homological mirror symmetry, which connect it to representation theory. In the same paper, Witten showed that underlying Transcendence theory is a two-dimensional conformal field theory associated to the Lie algebra and kappa, the WZW model, which has affine Lie algebra symmetry. We'll actually take this as the starting point. Okay. Oh, my video is off for some reason. Is that correct? What happened here?
Yeah, if you wouldn't mind trying to turn on your...
I don't know what happened. Okay.
There
All
we
right. Go. Something happened. Good. So this will be our starting point. Transcendence theoretic path integral on half space with the boundary, which is Riemann surface, computes a particular state in the Hilbert space of the theory based on the Riemann surface. The Hilbert space of Transcendence theory is the space of conformal blocks of the affine Lie algebra on the Riemann surface, which we'll call A, where the Wilson lines puncturing the Riemann surface translate into insertions of vertex operators. A conformal block, which obtained by path integral on half space with pairs of with half knots, the corresponding conformal block describes pairs of vertex operators colored by complex conjugate representations that come together and fuse to disappear. By varying positions of vertex operators on the Riemann surface as a function of Transcendence time, we get a colored braid in the Riemann surface times Transcendence time. The Transcendence path integral computes a matrix element of the braiding matrix that takes the Hilbert space and the space of conformal blocks from one time slice to another along the path corresponding to the braid. Any link invariant can be represented as a matrix element of the braiding matrix of, between conformal blocks that describe caps and cups. This way, both braiding and fusion play an important role in the theory, braiding to get braids and fusion to describe caps and cups. The action of braiding on the space of conformal blocks also explains the skein relation that defines the Jones polynomial. In the SU2 theory, on a plane with 4 punctures, the space of conformal blocks we need is two-dimensional. Any three vectors in two-dimensional space have one linear relation between them, in particular these three vectors, and the relation between them expresses the characteristic equation of the 2x2 braiding matrix, and that coincides with Jones's skein relation. The braiding matrices and fusion matrices are known explicitly. To find them, one wants to think about conformal blocks as solutions to a differential equation. This equation is the one discovered by Aganagic and Homology in the early studies of conformal field theory. It's an equation with respect to positions of vertex operators. From perspective of the Aganagic-Homological equation, the braiding matrix is a monodromy matrix along the path and parameter space that the braid describes. This monodromy problem for the Aganagic-Homological equation was solved by in 1989 by Drinfeld and later studied by Kazan and Lustig, generalized by Kazan and Lustig, following works of Tsuchiya and Kanye and Kono in 1988. So they showed that monodromy matrices that reorder a neighboring pair of vertex operators are given by R matrices of the UQ quantum group corresponding to the Lie algebra G, and the constructions of these R matrices is canonical. Beyond the R matrices, beyond the braiding, one only needs to know the conformal blocks that describe cups and caps. These are certain very special conformal blocks. Firstly, in a special basis, the fusion basis, which diagonalizes braiding, where you first bring pairs of vertex operators together. A pair of vertex operators labeled by complex conjugate representations that fuse to not just an arbitrary representation in tensor product, but to the identity simply disappear. So that gives it a cap. Our starting point for categorification of link invariants is a realization of conformal blocks, which comes from quantum field theory in 2 dimensions, with n equals to 2 supersymmetry, and ultimately comes from string theory. Knight's homological equation and conformal blocks of the affine Lie algebra have a striking and much more rigid generalization that whose existence is actually easier to discover in string theory, and in some sense is explained by string theory. This generalization is a deformation that was discovered in the 80s by Igor Frankl and Nikolai Reshetkin, who showed that one can break conformal invariance of the affine Lie algebra while surprisingly preserving much of the structure provided by conformal field theory. If you take a Riemann surface, so we will take Riemann surface where conformal blocks live to be a punctured infinite cylinder rather than a plane. Because we'll be breaking conformal invariance, the two are no longer equivalent. Working on a plane and a cylinder are no longer equivalent. The deformation is based on replacing the affine Lie algebra by what's called the quantum affine algebra, which is its the one parameter deformation. The parameter we'll call h bar. This replaces the Knight's homological equation by the quantum Knight's homological equation, which is a difference equation. And we recover the KZ equation from the QKZ equation in the limit where you take the step of the difference equation to 1 and h bar to 1, keeping the level kappa fixed. So we have only really one deformation parameter, which we can think of as h bar. In the limit, you keep positions of vertex operators on the Riemann surface fixed. Like in the conformal case, the solutions of the QKZ equation may be obtained as correlators of chiral vertex operators, except that all the operators are Q deformed. And we'll call the solution of the QKZ equation we get in this way, the Q by sewing chiral vertex operators, Q conformal blocks of the quantum affine algebra. This structure turns out to originate from 2,0 little string theory in 6 dimensions, labeled by a simply list Lie algebra G, which one gets in the limit of type 2b string on an AD surface singularity, labeled by G. From now on, we'll take the Lie algebra that underlies Transcendence theory and conformal blocks to be simply laced. So LG is G, and it's one of these algebras labeling little string theory. There is a generalization to non-simply laced Lie algebras, but it involves extra steps, which we won't be able to describe today. So one wants to study the 2,0 little string theory on a 6-dimensional space, which is a product of the Riemann surface where conformal blocks live, of a 2-dimensional manifold D, which will be supporting our 2-dimensional defects, and an extra complex plane. The vertex operators on the Riemann surface come from a collection of defects in little string theory, which are inherited from D-branes of the 10-dimensional string.
Excuse me, Mina. When you say little string theory, do you mean the sort of local 0-2 theory that comes from type 2b at an AVA singularity?
Yes, we will just take G string to 0, keeping the string scale finite, and we keep the dynamics of the 6-dimensional theory finite. So we have a string scale. That's the usual thing that one calls this little string.
In type 2a, I think.
Well, there's a version for type 2 and type 2b,
Okay, sorry, thank you.
and they're T-dual because we are, yeah, so they're both in some sense in present. That's right.
Okay, excuse me, thank you.
Would you say again, on which space do you have this 6D theory?
It's the Riemann surface where conformal blocks live, times a two-dimensional space where the defects will be, times an extra complex plane.
Don't we have trouble putting this little string theory on arbitrary surfaces?
So right now we can just take everything to be flat.
Okay.
And the Riemann surface A is an infinite cylinder. And in fact, this little string generalization will only make sense for when A is just flat. It will not get general from genus Riemann surface and so.
Okay.
Yeah. So the D branes we need are D3 branes of type 2B string, which are at points of the Riemann surface where conformal blocks live. They're supported on D and at points of this transfer space, and at 2 cycles of the AD singularity. The theory on such D branes is a quiver gauge theory. That's the consequence of familiar description of D branes and AD singularities discovered by Douglas and Moore in 96. The theory will turn out to be a 3-dimensional gauge. The theory on the branes is a 3-dimensional gauge theory on D times S1, rather than simply 2-dimensional theory on D, because the Riemann surface contains a circle. So contributions of string winding modes make the theory effectively 3-dimensional. Alternatively, you can T-dualize. One of the results of my prior work with Andrei Okunkov is that one can get the fundamental solution to the QKZ equation that spans the space of conformal blocks of the quantum affine algebra from either the Coulomb branch or the Higgs branch of this 3-dimensional gauge theory.
Sorry, where are the 3 dimensions again?
Good. If you were to T-dualize,
Yes.
so you're not in the 0-2 theory, but in the 1-1 theory,
Yes.
then the 3 dimensions would be manifest. The D branes would be D4 branes on a circle times D. Okay. So well, after we T-dualize, it's this circle.
Sorry, this is a circle which is in what you called A?
Yeah. No, it's on A you have string winding modes. So defects are points on A.
Okay. Defects are points on A.
Yeah.
What are the other 2 dimensions?
Yeah. I'm going through this rather fast because I've explained it earlier and it's just sort of meant to connect. So this is actually the connection. Part of these connections was discovered in my work with Nathan Hausi, who's going to, I think, be a postdoc at the institute next year. So we can guess them from either the Coulomb branch or the solutions of the QKZ equation from either the Coulomb branch or the Higgs branch. The supersymmetric partition functions of the 3D theory on what one should think of as a long cigar times a circle, where in computing the partition function, you include holonomies for the U1 times U1 R symmetries in the big R symmetry group of the n equals to 4 theory on the D3 branes. Or D4 branes.
You were a little bit, you were not completely explicit about what D was before, but now D is a cigar.
Now we want to take it to be a cigar. That's right.
Okay.
The ranks of the vector spaces, which gauge theory you choose, determine the representation and the weight in that representation, which the Q conformal blocks transform. The positions of vertex operators are positions of the heavy flavor D3 branes in the 0-2 theory on the Riemann surface. D3 branes are points. The highest weight vector of the Brahma module is the phi Deliopoulos parameter of the 3D gauge theory. It comes from a complex scalar field in the 2-0 theory, which abelianizes. The fact that, so this means that the bulk lives in a broken phase. And that's important because it means that all the complicated dynamics of the bulk theory is not important.
Sorry, is the broken phase the Coulomb phase? Oh,
Yes. Sorry. Of the bulk. Now, which solution of the QKZ equation the partition function computes depends on the choice of boundary conditions at infinity. The fact that one can obtain the partition function solutions of QKZ equation from either the Higgs or the Coulomb branch is a consequence of three-dimensional mirror symmetry, which implies that with two double identifications of parameters and boundary conditions, X and X check are interchangeable. If we were to pursue the story further, rather than discovering knot invariants, we would discover integrable lattice models. And in a sense of a very general kind. And this is the key result of my work with Andre. We won't go that path. Instead, we want to return to the question of our main interest, which is to obtain superstring realization of conformal blocks of the affine Lie algebra. Conformal point particle limit of little string theory, in which it becomes the 0-2 theory with conformal symmetry, turns out to coincide with conformal limit of the quantum affine algebra. In the point particle limit, the winding modes that made defects three-dimensional instead of two-dimensional become infinitely heavy. So as a result, in the conformal limit, the theory on defects in type 2B string theory becomes a two-dimensional theory on D. It's surprising, but it's by now well understood that there are different two-dimensional limits a three-dimensional gauge theory can have. The point particle limit of little string theory specifies which two-dimensional limit of the three-dimensional gauge theory we need to take. This is also the limit in which QKZ equation becomes the KZ equation. The limit turns out to be the one, not to be the one that takes the three-dimensional gauge theory to two-dimensional one, but rather the one that would do this for its 3D mirror theory. The resulting theory gives a description of two-dimensional defects of the 0-2 conformal theory, and it's not a gauge theory. One description of the theory and the defects is as a supersymmetric sigma model with a hyperkähler target, which was the Coulomb branch of the three-dimensional theory. This is because it's the natural two-dimensional limit of the 3D mirror theory. So supersymmetry is broken from to n equals to 2 in this description by rotations of the transverse complex plane with parameter related to kappa. That symmetry rotates the scalars and vector multiplets, and it also scales the holomorphic symplectic form on the Coulomb branch X. The symmetry is part of a larger symmetry of torus symmetries that act on the Coulomb branch, which include phi to Laplace parameters of the original 3D theory. From perspective of X, conformal blocks are partition functions of a supersymmetric sigma model on the very long cigar, where the sigma model is deformed by twisted masses associated with
Mina, what is lambda, capital lambda?
Lambda comes from phi to Laplace parameters, and it determines the rate of the Verma module.
But lambda is a torus, it seems.
Lambda is
torus or a lattice? I'm confused.
Lambda is a torus. It's a torus of rank of the Lie algebra LG. So you have as many parameters as as the nodes of the quiver as the rank of the LG.
So I'm pretty confused. These are acting as hyperkähler isometries of curly X? Yes,
they preserve the 2-0 form. But the one related to Q scales.
Well, that's not the same thing. Sorry, that's holomorphic symplectic. That's not the same as hyperkähler isometry. That's what's confusing me.
So we'll break hyperkähler symmetry.
Okay.
One has Q breaks it. As soon as you turn on Q, hyperkähler symmetry is broken, which is what makes the theory interesting.
Actually, they're not even holomorphic symplectic because they scale the 2-0 form.
In the interior, one has of the cigar, so the conformal blocks are partition functions of the sigma model, where in the interior of the cigar, you have A-type twist, And at the boundary at infinity, you place B-type boundary condition. The infinite length of the cigar makes A-type supersymmetry in the interior compatible with any supersymmetry on the boundary, even of B-type. From perspective of X, the Coulomb branch, the Knizhik's homological equation is what's called the quantum differential equation for flat sections of a connection on a vector bundle whose fibers are homology of X over the complexified moduli space that was introduced by Giventhal in his works on mirror symmetry. The fact that for the Coulomb branch, quantum differential equation and the Knizhik's KZ equation coincide is a theorem of a student of Andrei Okunkov, Ivan Danilenko. He's a postdoc at Berkeley right now. One gets different solutions to the quantum differential equation and to the Knizhik's homological equation by choosing different B-type branes as the boundary conditions at infinity. These boundary conditions form a category, and the category of boundary conditions for our theory, preserving B-type supersymmetry, working equivariantly with respect to this large torus, is known as the derived category of T-equivariant coherent sheaves of X, as was explained in the works of Douglas, Aspinwall, Horry, and probably many others. Since the KZ equation is the quantum differential equation, the action of braiding on the space of conformal blocks is monodromy of the quantum differential equation along the path in its scale and moduli corresponding to the braid. Braid group acts by autoequivalences of the derived category, because along the path and Kalen moduli, the category of B-type branes stays the same, while the individual branes change. It follows that the path interval of the sigma model, where you take the time to run along the annulus, computes the matrix element of the monodromy matrix of the KZ equation between pairs of conformal blocks corresponding to the chosen pair of B-type branes in the boundary. And if we take the same path interval, but think of the time as running around the circle, then it computes the index of the supercharge preserved by the two branes. The cohomology of that supercharge is the space of supersymmetric ground states. It's computed by this derived category as its most basic ingredient, the space of homes or morphisms between a pair of branes. So far, we understood how to get from the category of B-type branes that it manifestly categorifies braiding matrix elements of the quantum group between any pair of generic pair of conformal blocks. With help of mirror symmetry, I show that along with braiding, fusion has a natural geometric interpretation in the category of B-type branes in terms of certain perverse filtrations that were envisioned by Roque and Chuang, which describe the structure of the category of branes as one brings pairs of vertex operators together and a manifold develops a singularity in its scale and moduli. One of the things one learns is that the branes that describe caps and caps are simply branes supported on certain very special vanishing cycles in X. What makes these cycles special is the same thing that makes the trivial representation special. And these branes are automatically eigensheaves of braiding with the right eigenvalues. So using very special properties of these perverse filtrations and the vanishing cycle branes, well, the technology of Roque and Chuang is such that it makes it easy to show, to study derived equivalences. And it's not difficult to show that homology groups manifestly categorify corresponding UQ link invariants.
Sorry, Mina, what was calligraphic capital U?
It's the brane. These are the branes that correspond to caps and caps. The actual branes that sit on vanishing, they're not some abstract objects in the derived category. The actual brane structure sheaves a vanishing cycle. B brane on a vanishing cycle. And that fact that they're actual geometric object is why the whole theory is actually geometric and not just some abstract algebraic thing.
This is the vanishing cycle in the Coulomb branch, if I'm following at all.
Yes, that's right.
Is there like an elementary one for each cup and cap?
You can generically, we can say what it is. So The story works well for minuscule representations, and then the caps, each elementary cap colored by some representation is based on a minuscule Grassmannian. And one can show it. This Coulomb branch has a lot of connection to representation theory. A mathematician studied slices in the Affine Grassmannian, and it's one of the sort of key things in geometric representation theory and geometric Lagrange. So the fact that there's lots of representation theory there is not surprising at all.
So you're using the BFN description of the Coulomb branch, is that right?
Actually, what I use here is mirror symmetry to teach you how to think about the Coulomb branch. The description, no, not the BS, the other slices, the slices in the Affine Grassmannian as appeared in the works of Edward Witten with Anton Kapustin as spaces of Hecke modifications. That's the more useful description for this story, not the BFN Grassmannian. Recently, Ben Webster proved that link invariants that come from the category of B-type branes that I formulated are equivalent to the invariants he defined in 2013 using algebras studied by Khovanov and Lauda, Roque, and himself. Okay. As stated, however, neither the approach by derived categories of coherent sheaves, B-type branes on the Coulomb branch, nor by these algebras discovered by mathematicians earlier, is very computation friendly. In the rest of the talk, I'll describe how physics lets one reformulate the problem and solve the theory. And the description we'll get is completely new. The conformal limit is not a geometric limit from perspective of the Higgs branch of the three-dimensional gauge theory. The limit results in a badly singular space because it turns off its scalar variables. So we won't get anything based on X check. What one gets instead for free is a Landau-Gisberg model whose target is an open subset of the symmetric product of copies of the Riemann surface that's visible in type 2B string with a potential. The potential comes from a one loop integrating out of charged matter from the 3D gauge theory and taking the limit. It's a multi-value holomorphic function on Y, on the symmetric product of these Riemann surfaces. It has a part that originates from integrating out charged matter in 3 dimensions, and a part that comes from phi Laplace terms. Similar Landau-Gisberg models were studied by Edward and Witten and David Gayota, and also by Greg Moore and others. The difference with respect to the potentials you had written down is very modest. It is the term that comes from phi Laplace terms, but it's crucial for mirror symmetry. Actually, one can.
So, Mina, if I could stop
say
you.
just one thing, which is okay.
Mina, I'd just like to ask, since you alluded to that. So, yes, so that's a very similar superpotential that appeared in the Gayata-Witten, where you had logs of differences of points. And then Dima and I showed that.
Can we not go there, because I
that
want
one
to tell the story?
we couldn't
wait
check.
till connections till the end, I think it
Okay.
would be useful. Great.
We'll also have a discussion afterwards, Greg.
Yeah, there'll be a discussion afterwards. So let me just tell the story. I just wanted to tell you that this is reminiscent of something you've seen. The relation between the Coulomb branch X and Y is a cousin of ordinary two-dimensional mirror symmetry. It's not ordinary mirror symmetry because the space Y is half the dimension of the Coulomb branch. Instead, the Coulomb branch, which has a core locus, which is half its dimension, and which it contains all the interesting information about the geometry. Because we work equivariantly with respect to the symmetry that rotates this transverse complex plane, which rotates the scalars in vector multiplets. Okay, locus X is the locus preserved by this action. Okay, so it's a locus where complex scalars on the Coulomb branch are turned off because they're massive. So from now on, we'll call the full Coulomb branch the big X and the core locus the small x. The notation is unfortunate, but it's stuck. So on general grounds, by the origin in three-dimensional gauge theory, the small x and y are related by T-duality or mirror symmetry. The core locus, small x, embeds into the big X as a holomorphic Lagrangian submanifold, while the ordinary mirror of the big X, the big Y, fibers over the small y with homomorphic Lagrangian C star fibers. So there's pairs of mirror symmetries, one upstairs, one downstairs, in principle. Now, the bottom row has as much information about the geometry as the top. So we'll call the diagonal the equivariant mirror symmetry. That's what I'll mean by it. So in particular, the small y is the equivariant mirror of the big X. A model example to keep in mind is the big X, which is a AM surface singularity, the Coulomb branch of a U1 gauge theory with M hypermultiplets. Its core looks like a sausage with M-1 P1s and a pair of infinite disks attached. The ordinary mirror of the big X is big Y, which is a multiplicative AM-1 surface with a potential which we want. But this mirror, the multiplicative AM-1 surface, is a C star fibration over Ry, which is an infinite cylinder with M marked points in the interior. And at these marked points, the C star fibers of the big Y degenerate. There are M-1 Lagrangian spheres in the big Y, which are mirrored to M-1 vanishing P1s in the big X. And they project to Lagrangians on Y, a small y, that begin and end on the punctures. So in this case, Y is a single copy of the Riemann surface where conformal blocks live. And positions of vertex operators are where the fibration degenerates. By SYZ mirror symmetry, the mirror pair, the small x and the small y, share a common base, which is just a line with marked points. The fibers over this, in the case of small x, are holonomies, are dual photons in the case of small x, and holonomies of the 3D gauge fields around the S1 in the case of Y. So from the mirror perspective, conformal blocks of the affine Lie algebra are partition functions of the B-twisted theory on an infinitely long cigar with A-type boundary conditions at infinity corresponding to a choice of Lagrangian in the target. Mirror symmetry predicts that conformal blocks are partition functions, of the B-twisted theory with A-type boundary conditions at infinity. And such amplitudes have the following form, where omega is a top holomorphic form of Y on Y, W is the lambda Gisbert potential, and phi is some chiral ring operators. The conformal blocks one should think of as generalizations of pi stability central charge of A branes. The generalization is by inserting vertex operators and working equivariantly, which turns on the superpotential. What we've discovered here for mirror symmetry is the integral formulation of conformal blocks of the affine Lie algebra, the free field formulation that goes back to works of Fagin and Frankel and Schechtman and Varchikov. In fact, the B-twisted lambda Gisbert model and the A-twisted sigma model on the big X, working equivariantly with respect to T, are equivalent to all genus as topological string theories due to a reconstruction theory of Gieventhal and Telemann, which says that starting with genus zero data or the quantum differential equation, solutions of the quantum differential equation, you get to reconstruct all genus topological string amplitudes in a semi-simple 2D field theory, which these are. All right, so now corresponding to the solution, to a solution of the KZ equation, is, as we said, a brane at the boundary at infinity. Brane is an object of the category of a branes, which is the derived Foucault-Seidel category of Y with potential W. Okay, this from Y, which is the symmetric product, you need to delete a certain set that gives rise to a collection of one forms on Y with integer periods, which are responsible for equivariant gradings of both the branes and the humps between them, and mirror a similar structure on X. Now, mirror symmetry helps us understand exactly which questions we need to ask to recover homological and not invariance from Y instead of from big X. Now, since little y is ordinary mirror of the little x, we should start by understanding how to recover homological invariance from little x instead of the big X. That's actually a standard construction. Every B-type brane on the big X on the upstairs space which comes from a B-type brane downstairs on small x. Sorry, all the branes that we will need on the big X upstairs come from branes downstairs, okay, by some functor that takes the category of branes downstairs, upstairs, okay, by simply reinterpreting the brane downstairs as a brane upstairs. It turns out that this functor has an adjoint which goes the other way, that takes the brane upstairs to a brane downstairs, which basically works by restriction. The adjointness of these functors means that you can relate the computation of Holmes upstairs to Holmes downstairs as follows. For any pair of branes upstairs that comes from a pair of branes downstairs, okay, the Holmes between them upstairs agree with the Holmes downstairs after replacing one of the downstairs brane by a funny brane that you get by starting downstairs going up and back down. And that functor is not identical. So the identification between upstairs and downstairs computations is not a simple one, but it's a canonical one. By mirror symmetry, there's the same structure on the small y. For every pair of B-type branes upstairs on the big X, they come from branes downstairs on the small x. There's a pair of A branes on the mirror of small x, which are related by mirror symmetry, such that the Holmes upstairs and downstairs agree. These functors on the A brane side relate objects upstairs and downstairs in a way that mirrors what happens for the B branes. So now in our example, where y of y, which is equivariant mirror to big X, the AM minus 1 surface, mirror to I vanishing P1 in X is a Lagrangian, which is a simple line between a pair of functors. The functor that goes up amounts to pairing a brane downstairs with circle fibers over it, which is how you get these P1s upstairs from branes downstairs. It's something, yeah. Anyway, the functor that goes the other way does not send the vanishing sphere upstairs back to the simple interval brane, either computing it by mirror symmetry or by its definition, which one can give just purely in terms of the A model, one finds a figure 8 Lagrangian. So the brane you get by starting with a simple interval brane, taking it upstairs and back down, that will preserve the Holmes is a figure 8 brane. The fact that you get to preserve the spaces of ground states is not difficult to see. In the A model there, as we'll review in much more detail, the intersection points between Lagrangians. And one can see clearly that this preserves the intersection points. These two branes intersect over a single point. And the self-intersections of an S2 is cohomology worth of the S2. So there are these 2 points. So this preserves the Holmes. The example is relevant for Khovanov homology. if you want to obtain a link by closing a braid with 2D strands, the corresponding X categorifying Jones polynomial, the corresponding X is a Coulomb branch of an A1 quiver gauge theory with a quiver that has rank D gauge group and twice as many hypermultiplets, corresponding to being able to pair up all the strands by cups. The corresponding Coulomb branch, it turns out one can describe it, and this is highly non-trivial, as an open subspace of a default symmetric product of copies of the AM-1 surface, or more precisely of its Hilbert scheme of D points. This is a helpful observation, helpful but non-trivial. It's a theorem by Manolescu. So X, the big X, is also a symmetric product, just as Ry is a kind of a cousin of symmetric product. In the big X, the branes that close off the strands are supported on a vanishing cycle that is the product of D non-intersecting S2s. So each cup actually corresponds to a P1 in the AM-1 surface. And you have to take them to be non-intersecting to reproduce this picture. Now, the equivariant mirror of the big X is an open subset of symmetric product of D unordered points on the Riemann surface where conformal blocks live, with a specific potential. So now before we wrote down the general one, this is a special one for Khovanov homology and for the Jones polynomial. By equivariant mirror symmetry, the D cups are products of D non-intersecting figure 8 Lagrangians, and the D caps are interval branes, interval Lagrangians. In the Landau-Ginzburg description, both the Lagrangians and the action of braiding on them is completely geometric. So in fact, we can simplify the description of how you go from knots to Lagrangians by simply starting with a projection of a link to our surface and translate it to a pair of Lagrangians by choosing a bicoloring of the link by equal number of segments of each color, such that, say, red always underpasses blue. The mirror Lagrangians are obtained by replacing all the blue segments by simple intervals and all the red segments by figure 8 branes. So the figure 8 branes will give us one boundary condition, and the product of interval branes gives us the other boundary condition. By mirror symmetry, homological link invariant is simply the space of supersymmetric ground states between these pairs of branes. So in the symmetric product, the brane is also product. The space of supersymmetric ground states may be computed by Floer theory, which is modeled after Most-theory approach to supersymmetric quantum mechanics. The space of perturbative supersymmetric ground states is spanned by the intersection points of the two Lagrangians, and it's created by fermion number or Maslov index and equivariant degrees. Our Lagrangians are products of D one-dimensional Lagrangians on our Riemann surface. So the intersection points of pairs of Lagrangians are D tuples of intersection points of one-dimensional Lagrangians. So in this example, I have two Lagrangians, so you have to pair points to get intersection points. Taken after permutation, again, because we're in a symmetric product, or cousin of it. The action of the supertouch Q on the space is generated by instantons and squares to 0 in the absence of anomalies if the branes are consistent. The cohomology of the resulting complex is a space of exact ground states and the space of morphisms between the branes in the category of A branes. And the Floer approach to the A model, the coefficient of an intersection point in the action of the supercharge on another is computed by counting holomorphic disk instantons in the target Y, going from one point to another, of fermion number 1 and equivariant degree 0. because otherwise the disk doesn't close. Superpotential has to be well defined on that. In fact, it has to be regular on the disk. Right. That's simply the condition. The fact that the superpotential is regular on the disk is the condition that our disks avoid this set which we delete, and the disk is in Y. Now, a homomorphic map from a disk to the target Y projects on the Riemann surface to domains with non-negative multiplicities with boundaries on one-dimensional Lagrangians and vertices on their intersection points. So in this example, this is actually a disk between a pair of Lagrangians interpolating between the black point, black intersection point, and the green intersection point. Now, it turns out that one can read off from the domain, both from these domains on the Riemann surface. So instead of studying the high dimensional space Y, you can read off everything from the Riemann surface, both the fermion number and the equivariant degree of the map to Y. By using the fact that our theory is a close but distinct cousin of Heegard-Floer theory, which is a well understood and exactly solvable theory, understood by mathematicians. They've solved the A model for Heegard-Floer theory. We will get Heegard-Floer theory by replacing SU2, which we want for the Jones polynomial, by GL1/1, and it leads to Alexander polynomial rather than Jones's. It would arise from string theory by starting with type 2B string on the conifolds rather than on an A1 surface singularity. So there's actually a completely parallel story for the Heegard-Floer theory. It's developed and works with Miroslav Rabchak and his student Elisa Lepage. Now, the Heegard-Floer theory has a target, which is a symmetric product of D copies of the Riemann surface with a similar but different potential and a different deleted set. So for example, a Maslov index of any disk, you can read it off by studying the Euler characteristic of the corresponding domain and correcting it by contributions of the corners where the intersection points are. So this disk, for example, would have Maslov index 1. The index of the supercharge simply computes the intersection points of Lagrangians, keeping track of gradings. And in this case, we're just counting to compute just the Euler characteristic of the or the index of the supercharge. You just count the intersection point with some weights, and you get the result is construction of Jones polynomial by Bigelow from the 90s. And this theory explains Bigelow's peculiar construction. Now,
is MP in the previous thing? Sorry to interrupt. -1 to the MPP are the P's.
The M is Maslov index or fermion number. So it's just -1 to the fermion number, and then you weigh by covariant degrees.
Oh, thank you.
Sure. This rephrasing of the A model that counts holomorphic maps from a disk to target Y in terms of counting, in terms of calculations down on A, is really counting holomorphic curves inside D times A, which is part of our 6-dimensional target, with a pair of projections, one to the disk as a default cover and one to A to these domains. And that's known as cylindrical approach to Floer theory, and was developed in the context of Heegard-Floer theory. So it simplifies matters. So in this example, which we had was the right-handed Hopf link. There are 8 intersection points, and there are 6 domains that can contribute non-trivially to the differential. So each shaded domain is a domain that can contribute to the differential by just degree counting. So if all the maps are non-trivial, the homology of the above complex, together with the 3 remaining points, would give you Khovanov homology of the right-handed Hopf link. The fact that the differential squares to 0 comes, as usual, from contribution to Q square canceling in pairs, which come from broken maps of Maslov index 2 disks and equivariant degree 0. It's not easy. It's not difficult to see the dimensions of the complex of vector spaces which one gets with this differential coming from counting instantons grows polynomially in the number of crossings, which should be compared to exponential growth in Khovanov's case. I don't want to tell you. Okay, good. So it's much more efficient. Polynomial versus exponential. At the same time, the action of Khovanov's differential, even on much larger complexes, is completely explicit. Now, so to really compare, we need to learn how to count disks. In the cylindrical approach to Floor theory reduces the problem of counting holomorphic maps from disk to Y to a problem in complex analysis, one for each domain. It's a hard problem. Surprisingly, it can be solved. Not directly, however. The solution to this counting problem is by making mirror symmetry that relates the small x and the small y, or more precisely, their derived categories, manifest. So we will learn how to count disks. Working with derived Fokai-Seidel category as opposed to Fokai-Seidel category. So I will is actually simpler. For one, the derived category, the actual category of A-branes, has fewer objects because any deformation of branes that doesn't change the amplitudes is an equivalence. By contrast, in the Fokai-Seidel category, one only gets Hamiltonian isotopies, one for each individual brane, which is much fewer. In particular, one can generate the derived Fokai-Seidel category by a finite set of branes, which are thimbles of the potential. For every critical point of the potential, we get a pair of left and right thimbles, which are respectively the set of all initial conditions for upward and downward gradient flows of real W, real part of W. W is a holomorphic function. Equivalently, the Hamiltonian flows of imaginary part of W. The critical point equations for our specific potential coming from K's equation on this infinite cylinder are Bethan's equations with an irregular singularity at y is equal to 0. The solutions are isolated and non-degenerate and labeled by the weights. And the solution spaces are particularly nice when, as in our problem, the weight spaces are minuscule. The representations are minuscule. So these are you have as many critical points on Y as the dimension of the space of conformal blocks. The set of thimbles depends on the choice of chamber in equivariant parameter space. There is a choice of chamber that's suggested by mirror symmetry, for which the left thimbles are very simple. The left thimbles are simply products of real line Lagrangians, which, when the weights are minuscule, just look like this. They are just products of D non-coincident real line Lagrangians on the Riemann surface. They're mirrored to line bundles on small x. Mirror symmetry here works very much as mirror symmetry on just a cylinder. Asymptotically, this is just a cylinder. To formulate the homes between such branes, one has to deform them, as was discovered long ago by Horry and Buff already. After the deformation, all the intersection points become isolated. There are infinitely many of them. By mirror symmetry, there have to be infinitely many, because homes from any thimble brane to itself will have to describe the space of holomorphic functions on the mirror X, and that's infinite dimensional, but very concrete. The thimbles generate an algebra. They generate an algebra because the intersection points are not, the homes between them are not simply a vector space, they're a vector space with a product. One inherits the product from Floor theory. algebra elements, as it's actually easy to see from this picture, because asymptotically, we just have a simple cylinder, which is flat. The algebra elements the algebra elements all have cohomological degree 0. In particular, the action of the differential is trivial. This isn't an accident. It's a reflection of mirror symmetry, which maps these left thimble branes to line bundles on the small x. By Maslov degree counting, the algebra is an ordinary associative algebra graded by covariant degrees. So it's just the most simple ordinary associative algebra. While there are not many, in truth, nobody knows how to count disks. There are not many homomorphic, not many homomorphic disk counts, well, not directly. While there are not many homomorphic disk counts that one can evaluate explicitly, it turns out that all the ones that can contribute to the algebra are computable because they're products of triangles in flat space. And those are disks we know how to count. And then in particular, they're completely determined by the one-dimensional version of this theory.
You say again what higher product Spanish?
Because Maslov degree is 0, they would have to add up. The kth product would have to add up to k minus 2, but all the Maslov degrees of all the intersection points are 0. So the only product you get is the one that gives you the associative algebra structure. All the higher degrees vanish. The thimbles generate the category of the derived category of A-branes. So everything there is and everything there is to know about the thimbles is encoded in this algebra A. We get an equivalence of derived categories where d sub y is the category of A-branes, and d sub A is a derived category of A modules bounded from the left, which you get just from the functor that sends from this functor. So you can map every brane to an A module. The algebra A, this isn't that unfamiliar. The algebra, what this says is the following. The algebra A can always be thought of as a path algebra of a quiver, whose, for us, nodes correspond to critical points, and where paths from one node to another encode the homes, the algebra elements. So the equivalence says that our derived category of A-branes, or the category of A-branes, is simply the category of quiver representations. The whole brane category is as a simple category as can be of any kind of branes. The model categories that we always like to study. For us, thanks to this non-single valued potential, these quivers always have closed loops, in contrast to simpler, much studied theories, which come from single valued potentials, where quivers don't have closed loops and have much simpler representation theory. So our derived categories will be richer as they evaluate. For Y, which is the equivariant mirror of the A-1 surface, the algebra A is in fact the path algebra of a very familiar quiver, just the affine AM quiver, with unfamiliar relations, where instead of having the usual ones, you set the product of any two elements to 0. And this captures all the thimble intersection points and the relations between them. This familiar quiver, the more familiar version of this quiver, arises from B-type branes actually on the big X, the equivariant mirror of Y, where one also has a derived equivalence of this type, where the category of B-type branes is the category of representations of the quiver, where the algebra is now the familiar affine and quiver algebra with familiar relations. That's because we work on the big X, which is just the A-1 surface. Imposing instead the relation we need to get the algebra A for the thimbles corresponds to restricting the big X to the small x, whose category of branes of the small x is the category of modules of this algebra A. So in this way, homological mirror symmetry becomes manifest. Category of B branes and category of A branes are both modules of the same algebra. And this is how mirror symmetry, homological mirror symmetry is in fact, whenever you can understand it, this is how you understand it. It turns out we can, okay, the algebra A more generally is computable explicitly. It has flavors of the algebras that appeared in works of Khovanov, Lauder, Acquia, and Webster, and which Webster generalized in his algebraic approach to categorification. But the algebra and the description of how link invariants arise from it, which we'll end up with is simpler. Here's how we'll use the algebras. By virtue of the equivalence, the fact that the category of A branes is the category of quiver representations, or this algebra, any brane, any Lagrangian brane has what's called a projective resolution as a semi-infinite complex, each term of which is a direct sum of symbols in cohomological degree 0, but different equivariant degrees. What this means, the term maps in this complex are a prescription for how to obtain any brane, any brane you can write down by starting with the direct sum of symbols. There should be a shift by a cohomological degree here, which is missing. And gluing them by deforming the differential away from the trivial one. On symbols, the differential is trivial. You deform them away from the trivial one by giving expectation values to strings at intersections of symbols, which are tachyons. And the virtue of the derived category is that the original brane and the one by giving expectation values of tachyons are equivalent. For example, in the case of Y, which is the equivariant mirror of the A-1 surface, the figure 8 brane, which serves as a cap, can be written in terms of symbols. You need 4 symbols for that, as a complex with specific maps, which is quite literally a prescription for how to glue symbols at their remember, they intersect at infinities of the cylinder. So you'll stretch this picture out, okay, into symbols, give expectation values to the intersection points, and glue them up to a figure 8. This is also the complex that describes the corresponding brane on the mirror. In fact, this is how one discovered it, by understanding it first from the mirror and then deriving this figure 8, which is by translating the prescription through mirror symmetry. Now, our derived category has a second description in terms of the right symbols. The right symbols in the same chamber are instead variants of these simple interval branes. So from the right symbols, you get another algebra, which is essentially as simple as the original one. And in fact, because both set of branes, both the left and the right symbols span the derived category, you get a pair of equivalences of the category of A branes as modules of either algebra A or the algebra A check. The right symbols are compact and they're dual to the left, which implies that the algebra A check is related to algebra A by Koszul duality. And that gives you an algebraic way to understand this equivalence. This relation basically means that the branes simples of one are projectives of the other, which is what Koszul duality does, and has lots of important consequences for the algebras, which are true. The important part of this for us is that among all the right symbol branes are the branes that serve as caps. And that has a striking consequence. It means that we can get a second purely classical description of knot homology groups, that we can solve the instanton counting problem. We get a second description of knot homology groups, which we can read off from the description of the branes based on figure 8s as bound states of symbols. So this description of cap branes as bound states of symbols, which just encodes the classical geometry of the brane, lets you read off all the spaces of ground states without any work. It's just the cohomology of that. So it solves all the instant uncounting problems at once. So as for all branes, also for these branes that serve as cups, you get a description of the cup brane as a bound state of thimbles, obtained by starting with the direct sum of branes, of thimble branes, shifted by cohomological degree, and deforming the differential from the trivial one to the one that encodes these maps, which binds the branes. So that complex comes with just having the brane, or you can, anytime you have a brane, you can translate it into a complex of thimbles. From this complex, we get a complex of vector spaces with action of differential that squares to 0. So just from this line follows just by elementary algebra. The cohomology of this complex is, per definition, the space of ground states and the link homology. And it encodes all the differentials, all the discants and so on. So the 2 by yeah. So per construction, the vector spaces one gets at the kth term in the complex are spanned by the intersection points of equivariant degree J here and fermion number K. And they also span the floor complex. So this differential, constructed classically from the geometry of the brane, sums up the action of instantons, and it evaluates the floor differential. So this is how the equivalence between the category of modules and Y solves the categorification problem. The solution, which we did here for A1, for SU2, is not difficult to generalize for arbitrary simply algebra. Okay, so I'm over time.
Thanks for the lovely talk, Mina. And of course, well, let's ask if there are questions people want to ask now, and then later we'll adjourn for 10 minutes and meet on the other line to continue the discussion. But for now, any quick questions from what we've heard? I'm going to hold my own questions for after the more group.
So could you quickly say what changes if instead of thinking about SU2, you think about SUN?
The target is now going to be a product of symmetric products. And with the potential that talks to them both, but very gently. That's analogous to the sort of quiver description of the original gauge theory. So you just have to combine the pieces. But what's going to change is that, the theory has a little more ingredients now. If you think of this algebra in terms of some strings, there are strings of different colors. Mm-hmm. And otherwise, I don't think it's going to be much more difficult. I haven't written down that part though, but I don't think it's going to be any more difficult.
But sort of the size of so you're looking at a product of symmetric products, and sort of the mention of the space that you're looking at is proportional to n roughly. Is that the n in SUN? Is that right?
Yes, that's right.
Okay. Yeah.
That's right. That's how many symmetric products you need for SUN.
It's just thanks for the talk. I was just trying to understand this equivalence between cups and vanishing cycles in your very nice example where calligraphic x is am minus 1. Mm-hmm. So these cups are first of all added just on adjacent strands, or they can go from sigma to any other.
Yeah. So they're most obviously the vanishing cycles. If you bring the strands together,
Mhm.
But of course, you can act by braiding on anything, and once you understand what it is, right? To make any progress at all, you need to understand the braid group action. So you will understand such a problem to bring them into any position you want.
Exactly. Okay. So it's basically these two strands coming together give you a vanishing cycle in your
That's
total
right.
square.
That's right. So that's right. So a single strand colored by some minuscule representation corresponds to on the side of big X to a vanishing cycle that contains a minuscule Grassmannian as a factor.
Okay, cool. And by core of X, I guess you meant a deformation retract of the space X?
No, it's the locus preserved by the C star action. So it's it's a holomorphic Lagrange and it's half the dimension.
Yeah, it could still be a deformation retractor. So the only reason I'm saying this, it's very similar to what happens in the Hitchin moduli space, where you have an action you also have a C star action, and the deformation retract is the global nilpotent cone. Which is a Lagrangian and half-dimensional space as well.
So yes, because all you're doing locally, right? All the spaces look like R times S1 times a disk, and all we're doing is we're to some power. That's what a Coulomb branch looks like locally.
I see.
So X is just corresponds to sitting at the origin of that disk. So yes, it's a reprime.
So any more questions for now? If not, let's thank Mina again, and we'll meet in 10 minutes on the other Zoom link. If anyone who wants to participate doesn't have it, send me an email and I'll send you the other link. Thank you again.